Microsoft just made a chip that can hold a quantum state for a full 20 seconds, actually 1,000 times higher than what we were able to achieve with Majorana1. To put that into perspective, most standard quantum computers can barely manage a few milliseconds before everything falls apart. And this, by Microsoft's own standards, is a massive 1,000-fold jump from the milliseconds of their previous generation. And the reason it matters is not just a benchmark. It's because qubits, the building blocks of quantum computers, have one enormous fundamental problem. They break constantly. The moment you look at them, interact with them, or even let the wrong kind of vibration pass nearby, they're gone. So, let's try to understand two things here. First, what qubits actually are, not the oversimplified version you've heard before, the real one, in plain language. And second, understand what Microsoft just pulled off with Majorana2, why it's significant, and what the entire quantum industry could be racing towards in 2029. You've probably heard that quantum computers are powerful because they can be a 0 and 1 at the same time, that they process everything in parallel. That's a nice metaphor, but not actually how physics work. And that gap between the popular metaphor and the reality is where most misconceptions about quantum computing live. Because, if that were true, searching through trillions of possibilities would take no time at all. But that's not how it works. The reality is both stranger and more interesting. On regular computers, like your laptop or smartphones, everything, every photo, every message, every video is stored as bits. A bit is a switch. It's either off or on, 0 or 1. That's about it. Your laptop is doing billions of these switches per second. It's incredibly fast, but it's still just switches. The qubit is different. The qubit is not a switch. It's more like an arrow, a vector pointing somewhere in a three-dimensional space. While a single qubit mathematically exists in a 2D complex vector space, known as Hilbert space, its physical states map perfectly onto a 3D, real geometric space known as the Bloch sphere. When that arrow points straight up to the North Pole, it represents a 0. When it points straight down to the South Pole, it represents a 1. But here's the crucial part: it can point anywhere in between, anywhere on the equator or along the sides. That state of pointing somewhere in between is known as superposition, but superposition doesn't mean the qubit is secretly both 0 and 1 at the same time. What it actually means is that when you measure it, when you look at it, you get a 0 or a 1 based on probability. The specific angle of that arrow tells you the odds. Now here's why this is powerful. When you have multiple qubits working together, they don't just add up linearly. 2 qubits give you 4 possible states. 3 give you 8, 10 qubits give you 1024 states, and crucially, 50 qubits give you more than a quadrillion possibilities. As few as 300 qubits would give you more states than there are atoms in the observable universe. The state vector, which is the mathematical description of the quantum state, grows exponentially. And that exponential growth is where quantum computing gets its real power. And you can't just read all those states. When you measure a quantum system, it collapses. You get one answer, and that's the challenge. The art of quantum computing is designing algorithms that manipulate this exponentially large state vector. That's what Grover's algorithm does. That's what Shor's algorithm does. That's what every quantum algorithm is trying to do. The qubit is not magic, it's geometry. Now that you understand what a qubit is, let's talk about why building a quantum computer is such a big problem. And that problem actually has a name: decoherence. The qubit stays quantum only as long as nothing disturbs it. No vibration, no electromagnetic interference, no stray photons, no thermal noise. Even a single cosmic ray passing through it can knock a qubit off. Once a qubit interacts with its environment and loses its quantum state, it's just a regular bit, and the entire computation collapses. This is why quantum computers are capped at temperatures near absolute zero and around -273 degrees Celsius, colder than outer space. But even at those temperatures, the qubits are fragile. Their coherence time, how long it can stay quantum, is measured in milliseconds. But quantum operations are also extremely fast. Single quantum gates operate in nanoseconds, so you get thousands of operations before coherence is lost. The challenge is, to solve truly hard, commercially useful problems, you need millions or billions of quantum operations, and you need them to be accurate. Right now, we can't do that reliably. This is where Microsoft's approach matters. Microsoft said, what if we built a qubit that is fundamentally more stable? Not one that breaks constantly and needs correction. One that doesn't break in the first place. Their approach is called topological quantum computing, and it's based on a class of particles called Majorana fermions. Majorana fermions are fascinating for one reason. They are their own antiparticle. And when you engineer special quantum states using these particles, the quantum information gets encoded in not one location but across the entire system. This is called topological protection because the information is spread out. The local disturbance, a vibration, a noise, can't corrupt it. You'd need to disturb the entire system at once to lose the information. Last year, Microsoft unveiled the Majorana-1, the world's first topological quantum chip. It was a proof of concept. The community was excited but skeptical. Topological qubits had been theorized for decades but never demonstrated practically. In June 2026, Microsoft unveiled Majorana-2. Majorana-2's qubits have a mean lifetime of 20 seconds, with some instances lasting as long as 1 minute. For comparison, a typical superconducting qubit could last a few milliseconds. Majorana-2 is 20 seconds. Majorana-1 uses aluminum as its superconducting layer. Majorana-2 uses lead. In a quantum context, a lead superconductor helps shield fragile qubits from cosmic disturbances, the kind of random environmental noise that kills coherence. The team spent years figuring out how to incorporate lead without introducing new problems. Microsoft also used agentic AI through their Microsoft Discovery platform to accelerate the material research and fabrication processes. And Microsoft isn't the only one. As the ultimate heavyweight in commercial hardware, IBM operates the world's largest public quantum fleet, currently serving over 340 global partners while aggressively scaling its architecture through the 120-qubit Nighthawk processor and the highly flexible cross-chip connection Loon prototype. This rapid technical evolution anchors their ultimate 2029 milestone, Starling, a massive, fault-tolerant quantum supercomputer designed to reliably run 100 million gates across 200 logical qubits. So why does this matter? Let's be clear about what quantum computers will and won't do. They won't replace your laptop, browse the internet, play video games or write emails. They will be used for drug discovery and medicine. A fault-tolerant computer changes the economics of drug discovery entirely. Climate and energy. Designing better solar cells, quantum computers with the right algorithms can find the actual optimal solution. And then there's cryptography. Shor's algorithm, a quantum algorithm developed in 1994, can factor large numbers exponentially faster than any classical method. A fault-tolerant quantum computer running Shor's algorithm would break RSA encryption. The qubit is not magic. It doesn't do everything in parallel. It's a probability distribution encoded as a vector. It's geometry, it's physics. But when you build enough of them and keep them stable long enough, they start doing things that no classical machine ever could. Majorana-2 is not the finish line. It's the beginning of a more credible race.